All right, hi. My name is Pierre. I'm currently studying design and computation as a master's program in the University of Arts Berlin, also the Technical University of Berlin. And I'm presenting my paper I wrote together with Christoph and Sylvia Rothe. Both were my supervisors of my bachelor thesis I wrote last year. And this bachelor thesis we condensed down to the following paper of ours. The title of our paper is Diffusion-Based Sound Synthesis in Music Production. As a bit of a background why I started doing this, my bachelor's was in physics and computer science, quite technical, and besides my studies, I also did some music production, videography and photography. So I always wanted to combine those topics, and then I thought for a bachelor thesis this could be the perfect opportunity. And I thought music would be the best choice because there's this long history of influence from another. It's even dating back to Pythagoras. I really recommend this book if you want to check any more out on this history. But yeah, so generative AI has become more and more present the last 2 years. And we wanted to explore this field and usability in instruments and thus music production as a whole. For this, we built a digital instrument that uses latent diffusion to generate playable sounds. And around this, we came up with the following research question: are diffusion models suitable for use as a sound source in a music production process? More precisely, what we did, we explored the implementation of possible latent diffusion technologies and synthesizers, then analyzed the resulting digital instrument, and as well did an evaluation on the models in the context of music production. As a bit of motivation behind our project, I would like to take a quick peep into the current landscape of generative AI in music. So this came out, I think, a few months ago. It was after our product was finished. It's called Udio, and with it you are able to generate a whole music piece or a song from one single prompt. And I don't know, like the technique is really amazing behind it, but I feel like it takes away all the fun stuff in the artistic process, and there's not any decision making or creativity behind of it. And that's what we wanted to avoid firsthand. So our approach is that we are more for a hands-down approach, where the sound synthesis is done via generative AI, but the playing, the composition, all the fun stuff is still being done by the creative. We also wanted to explore the new soundscapes that offer diffusion, and also this new way of generating sounds. Another big motivation is that often creatives are in legal struggles because they use samples from other songs or maybe like from sound libraries, and this could be also a way to avoid these conflicts. So for related work, during our conception phase, we looked around what is similar to our idea, and we found that there's already a system existing that almost does the same thing. This is called Vroom AI and was developed during the neural audio plugin competition hosted by the audio programmer community. And it has less models than ours, and also no really options of settings or parameters. I'm going to show later that is in our product. Also, the resources from the community are really great in developing our plugin. So now for the background. First of all, synthesis. So synthesis is the generation and manipulation of musical sounds through electronic voltage. And the synthesizer is built of 3 main modules. So the source, where the sound comes from, in our case, is going to be the generative AI. The controls like a keyboard or knobs on the instrument, and modifiers that shape a sound. One of the most common modifiers is the so-called envelope, and there you have settings for the attack, decay, sustain, and release. So the attack is the time that it takes to reach the peak level of the sound. Then the decay is the time that it takes to go to a sustain level, and the sustain is maintained until you let go of the key, and then the release time is how long it takes to go back to null. To the diffusion process, so this is the generative AI that we use, and it has this inspiration in thermodynamics. And it's a process to train a machine learning model to seemingly generate images from random noise. And this is done by iteratively adding noise to a training image in the forward process, and then in the backwards process training to learn to remove that noise. This is normally happening on a 2D pixel space, but with latent diffusion, that space is shifted to a latent space, the so-called vector space, resulting in less computational heavy training and a faster inference, and also allows the inferring of the model via text or other modalities. Well, how does this translate to sounds? Well, you can treat sound as an image, a spectrogram. In a spectrogram, the frequencies of sound and the corresponding amplitudes are drawn against the elapsed time, and then they show the relation of different harmonies and define the timbre and sound characteristics. And these relations are the reason that notes from different instruments in the same pitch sound different. To now generate a sound, you can train a diffusion process to generate the spectrograms, and then in the end translate back into sounds. And this is the core idea of the diffusion models that we used, Audio LDM and Audio LDM2. There are many other sound generation models. This graph is already probably outdated, and some make whole sequences of music, some are specialized in voice generation, and a few of them are specialized in sound generation. We chose Audio LDM because at the time it was the most advanced and the most easy one to use across different type of devices. So both models were trained on a huge amount of audio data, and they're enabled to generate a wanted sound from a textual description. Both models use a latent space trained from spectrograms for the diffusion process, and in the second iteration, the conditioning of the model was reworked, enabling more input modalities and training with unlabeled data, promising better translation from these modalities into sound. Now to our instrument. The idea behind our instrument was to use these pre-trained diffusion models and build around them our digital instrument. We chose C++ as a language to achieve the minimal latency needed for audio programming, together with the JUICE framework and established C++ framework for programming audio plugins and synthesizers. To generate the audio signal from the C++ code would have been the most optimal to convert the pre-trained models into a binary file, but sadly due to the complexity and the use of different submodels, this was not feasible. And thus we opted to develop an inference service fast API in Python that the interface connects to and then generates sounds. So this is the resulting interface. I'm gonna demonstrate it live. So in the background, I have the diffusion server running. So now if I drag it in, I can open it. Yes. So down here you have first the selection of all the different models of Audio LDM1 and Audio LDM2, and then you have the option to choose a device. This is the torch device, and depending on your system, you have different options. If you have a Windows laptop or a computer with a CUDA-supported GPU, you can use CUDA. If you're on Silicon Mac, you use MPS, and in other cases, you have to resort to the CPU. So in my case, I'm on Silicon Mac. I will use MPS. I will initialize the model. Take a while. All right, now it initialized, and here I can define the prompt that I want to hear. For examples, I will input warm strings. Then you have the option to define negative prompts, so descriptions that you don't want in your finalized audio. Here you have the option to set the audio length. This is the number of inference steps, so these are the diffusion steps that are taken in the process, or the number of it, and also the guidance scale. The guidance scale tells the model how well it should adhere to this description. So higher guidance scale is a more strict correlation between the prompt and the final audio. I will change it to 4. And then I can generate my sample. All right, so as a little nod to the latent space in a spectrogram, I also included a spectrogram here and the waveform. And now you're also able to set the attack, sustain, decay, and release of the generated sample. There's also the option to tune the sound, because you don't know in which pitch the resulting audio is going to be, and to have a correct MIDI mapping, you can then tune the generated sound. Also, you have the option to make it louder or quieter. So now if I take the keyboard, I should be able to play some sounds, or I'm not hearing it. Ah, yeah. Thank you. So this is the turn down, sorry. So this is the interpretation of the model for warm strings. It may sound a bit weird, but I'll come to that later again. So, in addition to the development of the instrument, we also conducted a very small study consisting of 6 participants with varying degree of knowledge in music production. And we posed questions about the quality of the sound and how well the generated audio matches the input prompt while changing different parameters but having a constant generation seed. One parameter is the torch device. As I already told you, it's depending on the system you're on, and from this we found that if everything is consistent, and you change the device, the sound is changing, so there's no consistency in that. The guidance scale, we found that the most optimal value is around 4 to 5. For the diffusion steps, we found that a higher number seemed to deteriorate the sound and accuracy of the prompt, and this could be attributed to the fact that adding more information to a fully generated image yields no additional value, merely supersedes existing details. And the observed sweet spot, depending if you want a higher accuracy or sound quality, lies between 10 and 50. For the duration of the generated audio, it seems not to affect the quality or the accuracy too much, but what I personally observed is on longer audios there was this pitch shifting or pitch drifting over time, but this could very well be a desired trait based on the sound you want to create. The more interesting part of the study is we tested different scenarios for music production. The first thing that we tested is we wanted to generate single audio events. For example, a single kick drum or a single snare hit. And in that, the models did not perform so well, partly because of the training data, and this training data was most of the time repetitive music, so that has no chance of comprehending what a single event is. Surprisingly, some simple effects like adding reverb or delay worked, and also sometimes emotion or mood seem to work. Specific sounds or instrument, for example, an 808 kick drum, did not work so well, so my guess is that there's more training data needed to train on specific audio production terms and context. And this is what I want to embrace also in the discussion. I would say at the moment the models are not good enough for precise synthesizing and more suitable for sound exploration. One can embrace the weirdness and randomness and from that craft unique sounds. Also, a nice fact about sound is this way for giving the images. A generated image with weird fingers or artifacts may be conceived as uncanny or weird, but sound can be further sculptured and transformed to effects and filters. An improvement to the models may be to fine-tune them. I don't know if you are deep into diffusion models, but there's a trend of fine-tuning the models with image of oneself or in a specific style, and then the model has that specific style. And a huge amount of audio engineers have their own sample libraries and could very well fine-tune the models to their likeness and approximate the model to their specific sound. Also, one drawback is that the model output is only existing 16 kilohertz. 44/1 or 48 kilohertz would be way more favorable. Then also, the sampler that we built was very rudimentary. So as already stated, we couldn't convert it to a binary file, so the packaging has to be the VST or the executable of the plugin and also this inference server. Thus you have to have a bit of knowledge in the command line to run the server, and I think many producers don't have that. And also one drawback is there's no loop points in the sampler at the actual moment. So normally in a sampler you can set like there's the starting point, there's the end point, I want to repeat that part that is missing. And most common samplers have that. And also an automatic tuning would be very nice. All this begs the question if implementation of a sampler is really necessary. One idea would have to be to have just an interface for generation. For example, like stable diffusion web UI or conf UI, and solely concentrate on the generation, not the playback. And then in the end give the user possibility to drag and drop their sounds into audio production environments or even outboard gear. Speaking of outboard gear, also an option would be to go the hardware way. Many musicians prefer knobs and tactile feedback, and it would be very well possible to build a physical instrument, for example with NVIDIA Jetson. I already tried if the models run on that, and they do. And then one could add keyboards and knobs to build a hardware synthesizers on which this process could take form. Besides the cracks and flaws, you are still able to generate usable sounds, and they may sound alien or weird, but in the spirit of Bob Ross, you can embrace those happy little accidents in music production to make something great. And if there's some time left, I could very well show this. I go back to Ableton. So last night I tried to build like at least one loop with different instruments, but because of this random nature of the instrument, it's very hard. But still I found something usable. So first of all, let me turn off all the effects. I also, for this, I chose the prompt warm strings. And I got this sound. I don't know about you, but that reminds me a bit of like jungle music from the 2000s. So I thought, let's go that route. And with sound effects, I came up with this sequence. And then it had to have some drums in it, and I simply inputted jungle type drums, and I had like an alright result. I had still to quantize it and to chop it up, but yeah, it's usable. Yes, so I would otherwise like maybe use it for some sounds in a composition, but not try to do a whole composition with it. And if you want to try any other prompts, feel free to do it now, if you have a nice idea for a sound. Any ideas?
We'll have time for one or two of these.
Sorry?
We'll have time for one or two of these, and then we have to move on.
What?
We will have time for one or two of these,
Okay,
and
sorry.
then we will have to move on.
Okay, perfect. Crazy? Crazy ducks? Okay. All right, let's hear what crazy ducks sound like. I don't know, like, not so much ducks for me. something else, maybe? No, this is only for sound synthesis, yeah. Backwards trumpet.
But in the sound generation, you could end up using these for like wavetable synth, or like you could set up an entire synth.
Yeah. Yeah, so it has the notion of backwards, but yeah, I don't know about trumpet also.
All right, we should probably move on to questions.
All right,
Let's thank the
yes.
speaker.
So,
We have time for 1 or 2 questions, and it would be best, Stefano, if you don't mind to set up while we're doing that.
Thanks for the presentation. My question is about the training set. I don't know if you mentioned or if I missed it, but as far as I understand, the output to avoid hallucination is very sensitive on the training data. What's the training data so far?
so I didn't train it myself, it was pre-trained, but I think it's from an online library of free sounds. So it has like some notion of music production, but I think it like a company like Splice, so any of the like big sound libraries would take that into hand, could like create decent outputs. Yeah.
I have a question while we're just getting the next computer connected.
Mm-hmm.
If you ask your model about pieces, does it generate instruments characteristic to that piece? For example, if I typed in Rite of Spring, would I hear something that sounds like an English horn, but is in fact a bassoon?
I would assume not so much for whole composition, but funny enough, like I tried some different artists. For example, I once tried John Carpenter, an analog style synthesizer, and it had some characteristics of some composers. I would say yes, but yeah, still for some distinct sounds, not whole pieces.
Cool, thanks. Any last questions? Then let's thank the speaker again and get ready for Stefano.